all devices generally communicate through the PLC. There's also other communication protocols, which are something that also don't have to worry too much about at the moment. Like Siemens has its own communication protocol. It's not Ethernet IP. However, they are becoming much more standardized, and there's becoming like a few communication protocols that are now like these are the ones you use. Whereas like back in the day, there was like basically like 6 different protocols that were competing for each other. Like some 10 years ago, they had like 10 different protocols that were all trying to compete and do like the same things that are going on that we have right now. Like DeviceNet was one of them. Allen Bradley had FlexIO, which I'm not sure if anybody's still using that. I don't know why they would. Serial communication was a big thing back in the day, which is not really a communication protocol. It's more of a way of transmitting the data, like the physical wires. So like, you know, we have an Ethernet cable. Well, before the Ethernet cable, there was serial connection, which was like these 2 wires, and you had to have a third ground wire that was grounded. And I think there was even a 4-wire connection. I also didn't deal much with it because since I've always dealt with new systems, like we didn't develop new systems with the serial communication. We only developed it with like new Ethernet IP type of networks and IO link and stuff like that. The IO link basically became popular whenever, kind of in the beginning of my career, you know, it was like a new hot thing. And IO link took over, and like one of the nice things with IO link is like it's easy to set up, and there's a lot more data going on there. Like if you want smart sensors, a sensor could tell you if it's overheating. All kinds of things can happen over that smart IO link, versus just like a normal sensor that just has on off and that's it. Literally like a smart sensor can keep track of how many times it's been on off, time of how much power it's had on itself. Like there's a lot of like compute that's going on inside of a smart IO link device. For example, this project here, one issue we had is the company the PLC that they installed, whenever they did this upgrade on these cells, they upgraded the PLC that has a limit on its nodes. So it can only have like 24 nodes. What does nodes mean? Basically, it just means Ethernet IP devices. So we can only have 24 Ethernet IP devices. We have 3 nodes per fixture, 3 Ethernet devices, the SMC modules that are there. So those SMC modules, each are a node. So they consume one of the nodes. So 3 times 16, we're at 48. That's just on our fixtures. That's not including the robot. The robot's a node. The HMI's a node. The other SMC module that's already mounted on that back of that control panel, another node. The power supplies are a node. The weld power supplies, each one of those are a node. So you see, we just added up to like over 50 something nodes there, and the PLC has the ability to do 24 only. This is like one other advantage with like IO link is technically one workaround that you could do, like if you have this PLC that only has 24 nodes, but we need 48, instead of us using Ethernet IP SMC modules, we could use IO link SMC modules, right? And then so you know one of those master modules, like a Balluff master module, you can wire from one of those ports to one of the SMC IO link modules. Basically looks exactly the same. The only difference is the communication protocol is different. The SMC module looks the same. So now here's the advantage with that. The Balluff master is 1 node. The Balluff master is only 1 node. However, it has 8 ports on it that you can hook up 8 different SMC modules to. So now you have 8 SMC modules and you're only consuming 1 node. Whereas now we're consuming 8 nodes with 8 SMC modules because ours are Ethernet IP. But since we converted the 1 Ethernet IP Balluff master module and using IO link SMC valves, now we're only consuming 1 node and we're able to control 8 SMC modules. So going back to the number, you said we need like some like, let's say 50 or 60, right? Now we just need, you know, if we have 8 IO link masters, or if we have 8 IO link ports on 1 master, then we just do the math for that. So now we need, you know, 8, 16, we're at 32. So 4 of them, 4 nodes would give us the ability to have 32 SMC valve banks on the network with only consuming 4 nodes. So you see the major reduction in the amount of nodes.
Yeah.
Then gives you the ability to be able to like purchase a smaller PLC, or like it's one way of working around. So we can either tell these guys, hey, you need to upgrade your PLC, like it doesn't have the capacity we need for this cell, or we have to go back and rebuy all IO link modules, IO link masters, all these things, right? So you kind of just like in this scenario, you find out what's the easiest solution. What's the easiest and lowest cost solution? Okay, buy a new PLC and slap it in there. Nothing else should have to change. You should be able to download the same program into it, everything like that. And you're buying 1 device versus now we have to buy all new SMC modules, which is like some 40 something SMC modules, you know what I mean? We're talking about $100,000 in SMC modules or some shit. So like for them going back to like communication and like the HMI needs to communicate to the PLC. Everything generally, it's standard practice that everything should communicate to the PLC. If it doesn't, it really should. The only times you don't want to do that is if you need something that's ultra high speed. So like say for instance, if we're adding a vision camera, we might want the vision camera to talk directly to the robot because we can't have any delay. We need like microseconds of speed. So if you gotta talk from the camera to the PLC to the robot, that creates a little bit of a delay. It's not much, but I mean it might introduce like 250 milliseconds, quarter of a second in the response time of the camera and the data getting back to the robot. But so like now let's go to like the PLC and the PLC talking to the robot. So the most base route a device needs for them to be able to talk to one another is they need to be on the same network, and then you need to point to the device, especially from the PLC. So generally your PLC will be your master, and it will be the one that like establishes the communication. You set your IP addresses of your PLC and your robot to be on the same network. Then after you set your PLC and your robot, now for them to establish a connection, you have to point to the robot. How do you point to the robot? In Allen Bradley, you add an Ethernet module. When I say you add an Ethernet module, it's an add-on at the bottom of the logic. So you log into the Studio 5000, and over in your left column over there, where you have like your programs and stuff like that, down at the bottom will be your communication, your networks and stuff. For a majority of popular devices, there's already ones that are installed into Allen Bradley, into Studio 5000. So you just say, I want to add a new one. You type in what it is, like a Yaskawa NX200 or whatever, right? It'll pull up a block. You just select, I want to use this block. After you select that you want to use that block, this is one of the next things and one of the most challenging things to make the communication happen, which is what we're actually dealing with yesterday, is you have to say how much data are we going to talk. So whenever you set up the PLC and the robot, we'll just say like me and you, right? If I say I'm going to talk to you a 5, you say, okay, I'm going to listen for a 5. Okay, this is the data size that we're talking about here. That data has to match like 5 and 5, 6 and 6, 7 and 7. They have to line up. If they don't line up, they'll throw a fault and saying there's a communication settings error or something. Now that sounds easy, saying 5 and 5. One of the issues is, and I don't know why this is still an issue and why it is the way that it is the data sizes are different. So like talking about dents and booleans and stuff like that, right? Well, on the PLC side, you have a double integer, right? Which means you're talking in 32 bits per array, but in the robot side, it's communicating in bytes. So now you have to convert the data types. You have to do a calculation to convert what is a dent versus like what is bytes. And so this is like a calculation. You have to look it up on the internet and like find the math for it, right? There's a math. It's like multiply how many ever double integers you have over here by this number, and then this will give you how many bytes that you have. So that's the really confusing part, because then if you don't align that, then it doesn't work out well. And then there's one other thing to add to that. So if you read like the Yaskawa documentation, it should call out and tell you how to do this. And like one of the things that it'll say in that documentation is, and this is where it's not easy, this is where it's not complete straightforward math, is in your documentation, it might say, do this math that I was just referring to, and then add an 8. It might be like, do this math, where it's like simple math, 8 times 80 or something like that, right? And then plus 8. So you have to do whatever math is, whatever you had on the PLC, I'm just using random examples though, times 80, whatever you have on the PLC times 80, and that's what you need to put in your robot, plus 8. Why do you put plus 8? Because that's what the documentation tells you. So it's not anything that you just know. If you set up enough Yaskawa robots, you remember that. You go, oh yeah, Yaskawa robot, I gotta put plus 8. I gotta do this math and then put plus 8. But that's after you do like many robots, and then you're like, you just got it down. Every brand kind of has like little like nuance, things like that. And then the next perfect example is like we did, we set up that communication between them, and this is something that is unique to the Yaskawa, that doing the ladder logic thing. So having to every single tag or every single data point that we made that we want to use in the code, we now have to add it in the Yaskawa's ladder logic to make it actually function in the PLC and in the robot side.